Hello everyone, I am Namrata Kashi from the Department of Electrical and Computer Engineering at the University of Florida, here to present my final project presentation for the subject EEL6509 Wireless Communication. The topic for the project chosen is synchronization in OFDM systems. In this presentation, we shall look at the introduction to OFDM systems, how a multi-carrier transmission system works. Next, we will look at the OFDM transceiver system and the blocks that constitute it. Next, we shall look at the need for synchronization in OFDM and the effects caused due to symbol timing offset and carrier frequency offset. Next, various synchronization techniques to estimate the value of STO and CFO will be studied and analyzed. The analysis will be done after a simulation of the programs using MATLAB. We shall look at a short demonstration of the programs that are executed. Next, we shall look at the basic synchronization procedure that occurs in general cellular systems. In recent times, we have seen various features such as video calling, video streaming, online gaming, and mobile TV which are accessible to us. These features are made available to us through the various wireless broadband access networks. This is possible because the systems in modern days are able to support high data rates of up to 20 MHz. And one of the main reasons behind this is OFDM, or orthogonal frequency division multiplexing. OFDM is a popular multiplexing scheme which are used to support high data rates. It works on the principle of a single wideband carrier being divided into a large number of parallel narrowband subcarriers, and these subcarriers can transmit data parallelly. OFDM supports multiple input, multiple output, or MIMO transmissions. These multiple paths suffer from fading effects, ISI and ICI, which are inter-symbol interference and inter-carrier interference effects. These also undergo phase shift. In order to overcome these effects, synchronization is needed at the receiver for any OFDM system. The main advantage of an OFDM system is its efficiency while dealing with multipath transmissions. This system is also robust against interference in multiple narrowband signals. OFDM finds application in various cellular systems such as 3G, 4G, LTE, LTE Advanced, or also mobile WiMAX, which is the worldwide interoperability for microwave access systems. As the need for data rate increases, single carrier transmissions become inefficient because of the problem of intersymbol interference and multipath fading. Intersymbol interference increases due to multiple signals coming in as LOS or line of sight signals or non-line of sight signals. When these symbols interact, there can be constructive interference or destructive interference, and this destructive interference leads to the effect of multipath fading. In order to compensate for all these effects in a single carrier transmission system, highly complex adaptive equalizers will be needed. Instead, A multi-carrier system would be a simpler solution, wherein in a multi-carrier system, a single wideband is divided into multiple subcarriers which are narrowband signals. These narrowband subcarriers in an OFDM can follow any of the modulation techniques such as the BPSK, QPSK, 8-QAM, 16-QAM, and so on. One important factor to note in multi-carrier transmission is that the orthogonality needs to be maintained among them. This orthogonality is needed to improve the spectral efficiency and reduce the inter-carrier interference effects. The diagram shows the basic structure of a multi-carrier system, where multiple symbols are transmitted via various frequencies such as F0, F1 to Fn-1. These are the narrow bands divided from a single wideband. This diagram shows an OFDM transceiver system, where the first half represents the transmitter followed by a channel, and then this part represents the receiver. In OFDM modulation, the input data is first converted into n parallel data streams with the help of serial to parallel converters. This parallel data is then modulated with the help of n carrier frequencies, which are orthogonal to each other. After modulation, all the n signals are added together to form the passband channel, which are then transmitted over the channel via antennas and power amplifiers. In the demodulation section, the technique first involves down conversion to form the baseband signal from the passband signals, and then with the help of the subcarriers and filters, the subbands are derived. It can be noted from this diagram that the local oscillators are replaced by the FFT and IFFT block in the receiver and transmitter respectively. We know that the output derived from an IDFT block is always orthogonal, and thus the use of local oscillators can be eliminated. Also, instead of the IDFT block, IFFT block can be used to reduce the complexity of computation and to improve the performance optimization. Therefore, IFFT block replaces the local oscillator in the transmitter, and FFT block replaces the local oscillator in the receiver block. Also, we note that there is a cyclic prefix added in the transmitter and deletion of cyclic prefix in the receiver. These are cyclic prefixes are guard intervals that are added in order to increase the length of the OFDM symbol. This is necessary because a few starting bits are known to get corrupted due to ISI and propagation delay at the receiver. Upon adding these cyclic prefix bits, they are allowed to get corrupted because these are discarded after transmission at the receiver end. One disadvantage of adding these cyclic prefixes is that the symbol rate slightly reduces. Now that we have seen how an OFDM transceiver system works, let us look at the importance of synchronization in these systems. We know that OFDM has orthogonality as its main characteristic in order to avoid phase offsets. So, when the orthogonality of a system is not warranted, It's